Okay, let's talk about section 4.2. The differentiability theorem. So basically in this section, we're going to just review the sum, difference, constant coefficient, product, quotient rules of a differentiability, derivatives plus the chain rule. Okay, so sum, difference, scalar coefficient, multiplication, quotient, rules plus the chain rule for the differentiability. So we're going to prove them, not just state them, because we already know what the statements are. So let f and g be real functions and alpha in R a number if f and g are differentiable at a point A, then f plus g alpha times f times g, and f over g, here we have a condition, g of a is not equal to 0. We only need g of a not equal to 0. F over g, they are all differentiable at a. And in fact means we have some further relation. Here we only say the derivative exists. In fact part, we will have the concrete relations among derivatives. The derivative of the sums is the sum of the derivatives. The derivative of scalar coefficient is the scalar coefficient of derivatives. The product rule is f prime times g, not g, a. F prime of a times g of a plus f of a times g prime of a. Okay, and f over g prime of a is f prime of a g of a minus f of a g prime of a over g square of a. Okay, so the routine rules. Okay, so we're going to prove one of them. We're going to prove the quotient rule, the scalar the sum difference, sum rule. Okay, so normally we always say sum rule, difference rule, scalar coefficient rule, product rule, quotient rule. We always say 5, but actually the difference rule can be derived from the sum rule plus scalar coefficient rule. You just consider the alpha as -1, so you get the difference rule. But so in this list, we don't list the difference rule. Normally, the standard trick is used to show the product rule, like what the textbook provide. The textbook provide the proof of a product rule. So we are going to prove the quotient rule. Okay, so you can read the proof of the product rule by yourself. The proof of quotient rule is very close to the proof of a product rule. So anyway, let's try to prove. We know that if g of a is not equal to 0, then there is a delta greater than 0 such that over a minus delta, a plus delta at g of x is never equal to 0, right? So that's the sign, preserving sign property. So we know that over a neighborhood is not equal to 0. Because of this property, we can discuss the differentiability, because the differentiability should be defined over, should be discussed over an interval. Okay, so we do have an interval so that the quotient makes sense. And next, let's compute the derivative. So fx over gx minus f of a over g of a over x minus a. Right? This is the computation before the limit, and then you take a limit x approaches a. Okay, so we find the common denominator to do the division. So g over x, g over a, x minus a. Here's fx gx minus fa g of x. Right? And next, so we are going to have fx ga minus, we are going to insert, we subtract faga plus faga minus fagx. Okay, this is the routine trick, very standard trick in this part. Okay, we just insert minus and plus part. Okay. Okay, then next, the numerator. Here we factor out the g of a, so we get fx minus fa g of a. And here's plus fa, you factor out fa, you have g of a minus g of x. We don't want the g of a minus g of x, so we have to switch the order. So we have g of x minus g of a parenthesis fa. Right? So we need this. We always use g of x minus g of a. Okay, and we divide it by x minus a, here x minus a, and the whole thing over g of x, g of a. Okay, so that's everything we have so far. Now we're going to use the assumption. Assumption says f and g are both differentiable. F, g are differentiable. At a. So at least, so g of x is continuous at a. So we know this one. And continuous at a. So let's check what we have. We have the limit x approaches a. This part exists. This limit exists. This is dependent on x. Okay, this limit exists. And this limit exists. Okay, and all other elements are just numbers. All other elements just numbers. So when we take the limit by the limit laws, fx over g of x minus f of a over g of a over x minus a. We start from the beginning, we put a limit. It is, you are going to distribute this limit to each part. You are going to distribute to 3 parts. So you will have f prime of a times g of a minus f of a times g prime of a over g of a squared. And that's it. That's quotient rule. Okay, so the quotient rule is almost same as a product rule. It's almost the same as a product. The proof. Okay, so if you want, you can go back to check the product rule in the textbook. That's the same thing. So let's assume you know how to prove the sum, difference, scalar coefficient, product, and quotient. I may select one of them and put it in the final exam, even though I don't discuss the concrete proof, but you're supposed to know how to prove it. Okay, I may just pick up one and ask you to prove. It's not that difficult. Alright, so this is a standard routine rule for the derivatives. And next, we're going to study the derivative of composition of two functions, which is the chain rule. Chain rule, let f and g be real functions. If f is differentiable at a and g is differentiable at f of a, then g compose f is differentiable at a, with the formula g compose f derivative of a is equal to g prime of f of a times f prime of a. Chain rule. Okay. Okay. So let's see. Remember that we have a characterization of a differentiability. Let me see what is the name of it. What is the number? Oh yes, on page 86, theorem 4.2, theorem 4.2. So f is differentiable at a contained in an interval I if and only if fx is equal to capital Fx x minus a plus fa with capital Fx continuous. Over I. Capital Fx continuous over I. Okay? So we can write this and capital F of A is equal to F prime of A. Capital F of A is equal to F prime of A. Right? So this is the theorem we're going to use to prove it, to prove this the chain rule. Okay? Okay, so f and g are both differentiable at a corresponding point, then there are intervals I and j such that, let's say something, f is differentiable at a contained in I, fi is contained in j, and g is differentiable at f of a contained in j. Okay, so you have a interval I, here's a, have interval j, Here's fa, your function f, and then you have r. I don't know what domain you have, so g. Okay, so that's a relation. The whole domain, whole interval is mapped into the second interval, j. Okay, then there are two continuous functions. Capital F, capital G, such that fx is capital Fx, x minus a, and plus little f of a. G of x is capital G of x, x minus f of a. Remember here, we assume it is differentiable at f of a. So here's a f of a plus g of f of a. So you're going to evaluate at the point f of a. Okay, with f of a equal to f prime of a, capital G of f of a is equal to g prime of f of a. Okay. Well. Then let's do the composition. G compose f of x. G compose f of x is g of f of x. It's in J, fx is in J, so by the formula, it is g of fx, x is f of x minus f of a, plus g of f of x minus a. Okay, so that's it. We just do the substitution here. Whenever you see x, you write fx. Here's fx, here's fx, here's fx. And fx minus fa, is equal to capital Fx, x minus a. This part is equal to the product. It comes from this condition. And plus g of f of a. Okay, so what we see the composition of gf is equal to this continuous function times x minus a plus the composition at a. So decompose f is differentiable at point A. And the evaluation of this function, of this continuous function at A, g of f of A is equal to the derivative of the composition of g and f evaluated at A by the same theorem. We just repeatedly use this same theorem. And g of f of A is g prime, so it is g prime f of A, f prime of A is equal to this, and we are done. See, that's actually just a direct application of this characterization of derivatives. Okay. So we finished this section 4.2. In the exercise of 4.2, you can try the problem 7 on page 94. Problem 7 on page 94. So it's a combination of a differentiation plus binomial stuff. Okay? The combination of differentiation plus a binomial stuff is very interesting. Okay, so this is 4.2, section 4.2. Now let's move to section 4.3. The mean value theorem. What is the mean value theorem? We compare the slope of the chord connecting two endpoints AFA and BFB, the slope of this chord, and then we parallel and move it. If the function is, if the graph is smooth, function is differentiable, then definitely at a certain point, this parallel line will be the tangent line, and the corresponding value is C. So the slope is f prime of C. So the f prime of C is equal to fb minus fa over b minus a. This is the mean value theorem, MVT. Okay, so you just compare the chord. That's all. The simplest geometric explanation, but the mean value theorem is extremely important. All right, so it connected the derivative with the values of at the endpoints. Okay, now let's solidly prove the mean value theorem. First, let's prove the row theorem. The row theorem. What is a row theorem? Suppose that AB in R with A not equal to B if F is continuous on AB, differentiable on the open interval AB. So we always say it is continuous on the closed interval and differentiable over the open interval. And there's one more condition. If FA is equal to FB, FA is equal to FB, it's a flat. FA equal to FB, you have flat, horizontal. Then F prime of C is equal to 0 for some C in open interval AB, not endpoints. We emphasize the C's in the inside. Okay. Okay, so how do we prove this? So first you have a continuous function. F is continuous over the closed interval. Every continuous over closed interval has absolute max and absolute mean, finite. So by the extreme value theorem, F has a finite maximum value. Capital M, and a finite minimum value. Little m on the closed interval AB. Okay, finite maximum, finite minimum. Two values. If capital M is equal to little m, if you just have one, the maximum is equal to the minimum, then F is a constant function. On AB. F is a constant function, then F prime of x is 0 for any x in the open interval AB. Anything, right? Uh, that's trivial. The other case, if m is not equal to m, capital M is not equal to little m, if you do have two different values, fa is equal to fb, that's a condition. Where is the condition? Here. So FAFB can only take at most one value. So there is at least a point C inside AB, different from AB, with such that f of C is 1 over m and little m. Because you have just one value, you can take at most 1 over capital M and little m. Then it means there is a C such that it will take at least one of them, right? It doesn't matter which one the FC equal. So let's assume in the textbook it says FC is a capital M. In my discussion, I will choose the opposite. So we will say without loss of generality. Without loss of generality. We assume that FC is equal to little m. FC is equal to little m. C is inside AB. Okay, now let's compute the derivative at C. The derivative okay, this is a derivative. Of course, we can choose h plus 0 plus 0 minus. We can study one-sided limit. H approaches 0 from right hand side, H positive. So here, keep in mind H is positive. FC plus H is different. Is different from C. So FC is a minimum. It's a minimum value. Over AB. So what? So fx is always greater than or equal to fc for all x in AB, greater than or equal to, right? So here we get f of c plus h minus f of c always greater than 0, greater than or equal to 0, and divide by positive h. It's greater than or equal to 0. So the prime f prime is greater than or equal to 0. And we can also let h approach 0 from the left hand side. Remember, in this case, h is negative. H is negative. A positive number over negative number, of course, is less than or equal to 0. We take the limit. But they equal to each other. They equal to each other. We assume f is differentiable. F is differentiable. At C. So they are equal. They are equal. One is non-negative, one is non-positive. They equal. The limit is equal to this one. They're both equal to 0, so which is f prime of C. So f prime of C is equal to 0. F prime of C is equal to 0. That's it. That is the proof. The proof shows that we will reach the at the minimum value, the slope is 0. If the minimum value is achieved inside the interval. If the maximum value is achieved inside the interval, then it's also 0. Okay, so in the textbook they use the maximum, but here we use the minimum. Same thing. All right. So this is a row theorem. Row theorem discusses the horizontal case. Horizontal case. Okay. Okay. So after this theorem, the theorem is very important. The proof is very, very short and great. It's very great. It's not that difficult. There's no tricks. And after that, we have two remarks. The remarks tells us we have several conditions about the row theorem, not condition, hypothesis. We have continuity, we have differentiability, we have FA is equal to FB. Those three hypotheses cannot be weakened. Okay, so first, the continuity cannot be relaxed. Why? Well, not why. I mean, we have a counterexample. Let's pick up this function. Of course, it's not continuous. It's differentiable over the open interval, but not continuous over the closed interval. So you have 0, 1. This part, you move it down. You redefine the right endpoint to be 0. Then we know that the derivative over the whole open interval is 1, but the FA is equal to FB. There's no point to C such that F prime of C is equal to 0. Right? So that's actually it's not continuous. You even don't have the extreme value. You do not have a maximum value. You have a supremum. You don't have maximum value. Okay, so continuity cannot be relaxed. And second remark, 4.14, it says the differentiability cannot be relaxed. Differentiability cannot be relaxed. So we do have this standard of whenever you have differentiability broken, you possibly will think about ops value of x because it's not differentiable at 1. It has a corner. Okay. Well, also clear. This continuous FA is equal to FB, but left part is a negative. Slope is -1. Right part slope is +1. So there's no there's no f prime of x equal to 0. Okay. Okay. Those are two conditions. Continuity, differentiability, they are essential in the row theorem. FA equal to FB, it just means you cannot take capital M and little m together. If you take a capital M and a little m, then there's no place you can find the global extrema inside it, right? And next, let's try to prove the mean value theorem. And here we actually prove an even stronger one. We call it the generalized mean value theorem, or the Cauchy mean value theorem. Okay, so suppose that A, B in R, well actually we assume A is less than B. Even though in the textbook it says A is not equal to B. A is not equal to B, you have two possibilities, A less than B, A greater than B. But based on the writing of the theorem, we assume A is less than B. We don't lose anything. It's a pure symmetry. The first statement is called the generalized mean value theorem. Generalized mean value theorem has two differentiable functions. Regular mean value theorem, like this one, it only has one differentiable function. Okay, so if fg are continuous, on the closed interval AB and differentiable on the open interval AB, then there is and n, there is a number C in AB such that f prime of C GB minus GA is equal to G prime of C FB minus FA. Okay? FB minus FA. And sometimes, I mean, we don't write this way. This way it looks not that symmetric. We write this way. F prime of C over G prime of C is equal to FB minus FA over GB minus GA. GB. Okay, this is symmetric. Okay, F prime over G prime is FB minus FA over GB minus GA. Okay. The mean value theorem, that's why it's called the generalized mean value theorem. The mean value theorem is a special case of it. So if F is continuous, on AB and the differentiable on open interval AB, then there is a C in AB such that f prime of C is FB minus FA over B minus A. Okay. First of all, okay, this is the statement. The statement of 4.15. 4.15. All right. So the proof will depend on the row theorem. There's no tricks. Well, there's a small tricks. We have to set up a clever function. We have to set up a clever function. But in general, the proof is a row theorem. First, I want to mention that the mean value theorem is just a special case of generalized mean value theorem. You let G to be constant function. Let G of x not constant, identity function. Let Gx be x. Then you can see that G prime of C is 1. GB minus GA is B minus A. Then part 2 is a special case of part 1. Okay. So mean value theorem is just a special case of when G is an identity function. Identity function. Okay, so nothing you need to prove. Okay, so everything we need is a proof of part 1. We prove part 1, we need to construct a continuous function over the closed interval, differentiable function over the open interval. A function at A is the value at A is equal to the value at B. All right, so that function has a formula more or less like this. What is a function? We have this function. This function h is continuous over the closed interval AB and differentiable over the open interval AB. The only thing we need to prove, we need to verify is that HA is equal to HB. HA is FA GBGA XA FBFA. What we have is FAGB minus FAGA minus GAFB and plus FAGA. Cancelled, so you have FAGB minus GAFB. This is HB, HA. HB FB GB minus GA minus GB FB minus FA. Well, let's see. This is a FBGB minus FBGA minus GBFB and plus GBFA. This term that cancels, so you have FAGB minus GAFB. So you have HB is equal to HA. Then by row theorem, there is a C in the open interval AB such that H prime of C is equal to 0, and you just compute what this is and you're done. Okay, so H prime of C is equal to 0. That's exactly equivalent to this part. And here GBGA, FBFA, they're constant. I'm sorry, here GBGA, FBFA, they're constant. When do the differentiation, you only do differentiate F and you only differentiate Fx and the G of x. Okay, so that's perfect. That's perfect. Very cool. Okay, so we're going to prove one example as an application of a mean value theorem, and then we finish this video. We prove that 1 plus x is always less than e to x for x positive. Of course, if you know the Taylor expansion of exponential function e to x, then this is 1 plus x squared over 2 plus x cubed over 6, whatever. So you have a lot of positive terms. Of course, it's strictly less than. But let's assume you don't know the Taylor expansion. How do we prove it? Okay. Okay, so let fx be the e to x minus 1, and then we fix x. Fix 1x, okay? Fix x, you see here, x is positive. This function is a nice function. It defines everywhere over the whole complex plane. Sorry, not complex. Over the whole plane. Over the not plane. Over the whole number lines. Over the whole number lines, we consider what? We consider the interval 0x. We fix it. We consider interval 0x. Then f is continuous over the closed interval 0x and the differentiable over the open interval 0x, then there is a c in the open interval 0x such that f prime of c is equal to fx minus f0 over x minus 0. The mean value theorem. Fx minus x0 over x minus 0. Alright. What is f0? F0 is ex minus x minus 1. What is f? This is fx. F0 minus e to 0 minus 0 minus 1 over x. E to 0 is 1 minus 0 minus 1 is 0. So you only have fx over x. So actually the right hand side, this is fx. So let's just write fx. We don't expand it. F prime of c. What is f prime? F prime is e to x minus 1. Evaluated at x equal to c. So this is e to c minus 1. E to c minus 1. So what do we have? So we have fx is equal to x times e to c minus 1. E to c minus 1. C in 0x. So c is greater than 0. C is greater than 0. E to c is greater than e to 0. E to c is greater than e to 0. Exponential is an increasing function. So fx is equal to x e to c minus 1. It's greater than 0. This difference is greater than 0. X also is greater than 0. So product is greater than 0. So you are done. You prove fx is always greater than 0 for all x positive. Right? For all x positive. And that's it. That's our application of the mean value theorem. We do find the relation between the derivative at a certain point between a and b and fa minus fb over b minus a. Fb minus fa over b minus a. Okay? Okay, so well, let's see. Okay, anyway, we stop this video here and we will continue another example of the application of mean value theorem in the next video. Thank you very much. We finish this video.